Hi everyone, welcome to lab 2 of ELEC 4503. In this lab we're going to design Coax-Fed microstrip lines. There's going to be four designs. The first one is the coax cable, and then the microstrip line, and then we're going to add the coax cable to the microstrip line in the edge mount configuration, and then the vertical through-hole configuration. In this demo, I'm going to show you how to design the coax cable and the microstrip line, and then your part of the lab would be to combine the two designs here. Alright, so we'll get started. So the coax cable we're going to design is shown here. The two dimensions that we would need to determine is the outer diameter and the inner diameter of the conductors, and we also need to know the dielectric filling between them. We are going to design this to have a characteristic impedance of 50 ohms, and you can use online calculators to help you with that. Alright, so the design will be on HFSS, as you guys know. I want you to simulate it between 1 and 4 gigahertz. I ask you to use Teflon as the dielectric, which has an epsilon R of 2.1, and I'm giving you the inner conductor diameter, which is 1 millimeter. The first question is to calculate the outer diameter needed to achieve a characteristic impedance of 50 ohms. So if you go to this website, so this is a calculator that uses this equation to calculate the characteristic impedance. The dielectric constant of Teflon from the lab manual is 2.1. The inner conductor diameter is 1 millimeter. And then the outer diameter is what we need to determine for a 50 ohm impedance. So that you can use trial and error. You can give an initial guess and see what you get. Of course, you can solve this formula for the outer diameter, and I couldn't find an online calculator that does that, but you can always do it on MATLAB or something. Alright, so initial guess, I'm going to say maybe 5. So when I do that, I get 66 ohms, which is higher than 50. So in order to get a lower impedance, I need to make this smaller. So if I go like 4, it's not exactly 50. Try 3.5. Getting close. 3.4. Getting there, maybe 3.35. 3.35 is the outer diameter. So just make a note of that. So outer diameter is 3.35 millimeter. Alright, so now that we know the outer diameter, we can go on HFSS and design it. So ANSYS Electronics Desktop. And make sure that the project is on the H drive. So if you do save as, if it's not on the H drive, make sure you go in there. Alright, so I will call it Lab 2 Coax-Fed Microstrip lines. And then I'm going to add an HFSS design. I'm going to call that coax cable. Alright, so as I mentioned before, first step is to design the 3D model of your structure. So for the coax cable, there's going to be 3 parts or 2 parts that we're going to draw. So we need the inner conductor, we need the dielectric, and we need the outer conductor. So in our case, the outer conductor, we can just define it as the surface of the dielectric. So we would need to design two things. So the first one would be the cylinder of the inner conductor. So if you click on draw cylinder, you can just put the cylinder somewhere in the solution space, and then we're going to go and define the dimensions in the next step. All right, so that's the cylinder. By default, it's a vacuum cylinder. First, we can give it a name. Call it inner conductor. And the inner cylinder is going to be the inner conductor, so we can change the material to copper. And then for the dimensions, the starting position we can leave it as the origin, which is fine. And let's say that we wanted to extend in the z-axis. So it's the length of the cylinder will be along the z-axis. The radius will be the inner diameter over 2. So we can create a new variable called dn over 2, and the inner diameter is 1 millimeter. And then the height or the length of the coax, that one I didn't give you guys a design spec because it can be as long or as short as you want, because it doesn't affect the characteristic impedance. So we can create a new variable called coax-h, and I'm gonna choose that to be something like 3 centimeters. And then if you press Control D, press on the solution space and Control D, you should be able to see the inner conductor cylinder. And I'm gonna give it a different color. All right, so that's the first part. Second part is to design the dielectric filling. So that we're gonna create another cylinder for it. And that would be the dielectric. And the material of the dielectric, as I mentioned in the lab manual, is going to be Teflon. So you can search for Teflon. It's right here. And as you can see, it has a relative permittivity of 2.1 and a loss tangent of 0.001. And that was the relative permittivity that we used in the calculator to determine the outer diameter. We press OK. And then we can go in here and start it at the origin as well, because we want it to be concentric with the inner conductor. The radius will be the outer diameter over 2. So we calculated the outer diameter to be 3.35. And then the height would be the same height as the inner conductor. And then I'm going to make that slightly more transparent so you can see inside. And there you go. So we have the dielectric filling, we have the inner conductor, and in case you missed it, these are the properties for the dimension, for the inner conductor, and for the dielectric, and the variables are under the design, and you can see them here. All right, so the next step is to define the outer conductor. So in this case, we can just define the outer boundary of the dielectric filling, and then define that boundary as copper. So if you press F on the keyboard to select faces, or right-click selection mode faces, that will allow you to select the outer boundary. And if you move this around, you can see, or you can just do a top view. You can see that we only selected the outer conductor of the cylinder. All right, so once you have that selected, you can right-click assign boundary, and finite conductivity. Over here, we can call it the outer conductor, and for the material, we're going to use copper. So you can search for copper right here, and then press OK. And if you go under the design, under the boundaries, you can see that outer conductor defined as copper. All right, so after you've defined the boundaries, the next step is to define the excitations. So for the coax cable, it's really simple. It's just the top part, the top circle here, and the bottom circle. These will be the ports of your structure. So again, if you press F, so you're able to select faces, you can select the cylinder here, or not the cylinder, the circle. You just select that face. So if you right click, assign excitation, waveport. So we can just leave it as 1, and we don't want to renormalize because we want the impedance of the waveport to be the same as the impedance of the line, and we're doing that so we can check what the characteristic impedance of the coax cable is. So you can press finish, and then do the same thing for the other side. So select faces, assign excitation, and leave it as don't renormalize as well. All right, once you have the excitation defined, you'll be able to see it under here as well. The next step is to define the solution frequency. So if you go under analysis, right click, add solution setup, advanced. So in the lab manual, I'm asking you to simulate this structure from 1 to 4 gigahertz. So the highest frequency of interest is 4 gigahertz. So we can set that as the solution frequency. And of course you can set it as anything higher than 4, but 4 is also okay. The maximum number of passes, we'll put that as 15, and maximum delta S 0.01. And under options, the minimum number of passes, we'll set that to 6, and minimum converge passes to 3. Press OK. And for frequency sweep, so we're interested in frequencies between 1 and 4. So an interpolating sweep is good for that because it's a wide frequency range. So we'll set the start as 1 and the end as 4. And the number of points, 401 is good, but we can also choose a higher value, something like 801. So that's good for the frequency sweep. All right, so we've set the frequency sweep, we've set the convergence criteria. Now we have everything we need to simulate the design. So if you click on the design, simulation, validate, make sure everything is correct, and then press on analyze all. I'm just going to hide the messages so you can see the simulation running. So while it's also running, you can look at the conversions to see where it's going. If you see conversions here, you can either look in the table or look in the plot. So you can see that we are below our convergence criteria, which is good. So this should be this should finish pretty soon. And because we specified the minimum number of passes to 6, it will run for at least 6 passes even though it has converged. And always remember to check the conversions before you look at the results. Okay, so the simulation is done. Now we can look at some results. So if you look at the lab manual, the first thing we want to look at is the characteristic impedance of the coax cable from 1 to 4. So if you go under results, we can plot the port Z0, which is the characteristic impedance of the line. And the reason why it would be of the line is because we selected the option to not renormalize the waveport. So we can look at the port Z0, and we want to check the real and imaginary. We can see what they look like. And for the solution, we're going to use the interpolating sweep that we just defined. So if you click on create new report, and you can see here the characteristic impedance is 50 ohms for the real part, which is what we expected, and the imaginary part is 0, which is also what we expected. So that means your outer diameter calculation was correct. All right, so the next result is to plot the S11 and S21. If you go under rectangular plot, you can select S11 and S21. We plot that in dB, and same thing, we're using the interpolating sweep. All right, so you can see here the S21 is almost 0 dB. So there's almost perfect transmission, and the reflection is really low from 1 to 4. All right, the next step is to plot the magnitude of the E field inside the coax cable at 4 gigahertz. So if you guys remember, in order to see the field, we need to run a discrete sweep. So if you go to analysis setup here, we can add a discrete sweep, but also remember that the solution frequency that you defined, which was 4 gigahertz, you will also have a field solution at that frequency. So we can either go and plot the fields now at 4, or if it's a different frequency than the solution frequency, we would have to add a discrete sweep. But since the solution frequency is 4 and we're interested in the field at 4, we can simply plot the field inside the coax cable. So if you go under dielectric, right click, plot fields E magnitude, and you can see here that last adaptive, which is your solution frequency, is 4, so we can plot the field at 4. So you can press done, and that's the E field inside the coax cable. As you can see here, there's a very high magnitude on this side, and that's because this is the port where the power is coming from. So if you right click on excitation, edit sources, you can see that the 1 watt is applied to the first port. So that'll be the source port. And we can also animate that field, see what it looks like. So if you go under field overlays, magnitude, right click, animate. And here you can see the power is being launched from this port, and it's moving down the line like that. All right, so that's the animation, and that's part D in the coax cable design. Part E is asking you to terminate the coax cable with a short or a perfect E boundary, and then plot S11 de-embedded to the short from 1 to 4 gigahertz on the Smith chart. So for that, you can edit this design, but what I prefer to do is to create a new design for any new problem that I'm working on. So you don't have to work on it from scratch. You can simply copy this design and then put it in the same project, and we can call that coax cable short, because we're going to put a short circuit. And so what we're going to do is we're going to delete the second wave port on the bottom, and instead of that wave port, we will replace it by a short circuit. So we can go ahead and delete that. So we only have one wave port, and then the other side, since it's not defined, if you guys remember, HFSS will assume that this side is, it will assume that whatever you don't define as a boundary, we'll assume it as a perfect electric conductor. And since we want a short or a PEC, we will just leave it undefined. So the bottom here, I'm going to leave it undefined. But since we want to find S11 at the short, we have to actually de-embed this port down to the short circuit. And to do that, if you double click on the port, post-processing, we can de-embed that down to the short circuit, which is simply the coax height. You press OK, and you can see here that all the results that you plot will be de-embedded to this side of the coax cable. All right, so once you have done that, you can resimulate. So you can right-click, Analyze All, or you can go under Simulation, Analyze All. All right, take a moment to think where you would expect the reflection coefficient to be on the Smith chart when we have a short and we're de-embedding to the short. And while we're waiting, we can also look at the conversions. You can see that it's very good. It's converged, and now it's working on the frequency sweep. Okay, so if you go under results, you can also check the port impedance. So you can see that it's not affected by the short, which makes sense. The characteristic impedance of the line stays the same. On the other hand, if you look at the S11, so in this case there's no port 2, so there's no S21, so we can go ahead and delete that. So S11, you can see it's very high, so it's very close to 0 dB, which makes sense because you've terminated the line with the short circuits, so there's almost perfect reflection to the port. But what we're interested in is S11 on the Smith chart. So if you go on here, Smith chart, so we can plot that. And if you expected it to be on this side of the Smith chart, so this red dot here, you can zoom in to see it. So it's right there, and that means it's a short circuit, as you would expect, because you terminated it with a short. So that's for a short circuit, and that's part E of the lab manual. So we can go ahead and save that. The next part is, actually before going into the next part, let's take a look at the field inside the coax cable. So this is not part of the lab manual, but we can also take a look at it. So what do you expect to happen to the E field if there is reflection? So you can take a moment to think about that, and we'll look at the animation and see if we can see it. All right, so if you expected there to be a standing wave, you are correct, which you can see here. There's going to be points that are null on the transmission line, like here and at the port, of course. And there's a standing wave that's happening due to the reflection. Okay. So we'll save that, and the next part is to do the same thing, but instead of a short, we will have an open circuit. So an open circuit is going to be a perfect magnetic conductor, because a short circuit is a PEC, and an open circuit is a perfect magnetic conductor. So we can simply copy the short circuit design, call it open, and now instead of leaving this side as undefined, which HFSS would assume is a PEC, we can define it as a perfect magnetic conductor, or a perfect H. So if you select faces, press F on the keyboard, you can right click, assign boundary, perfect H. Simple. And the de-embedding would still be to the open side. And we will also look at the Smith chart after we run the simulation. So if you go on simulation, analyze all. All right, so where do you expect to see S11 on the Smith chart? Well, first of all, do you expect the magnitude of S11 to change? So that's the first question. And do you expect the phase to change? Because the Smith chart plots magnitude and phase. So take a moment to think about that. And do you expect the characteristic impedance of the line to change? So we'll take a look at each one of those when the simulation is done. Okay, so simulation is done. Let's look at the characteristic impedance, and it doesn't change as expected. S11, so the magnitude of S11, you can view it here or on the Smith chart, but if you guys remember from the short, the magnitude will not change because either for an open or a short, you still have perfect reflection. What matters is the phase of the reflection. So for a short circuit, of course, the phase was 180, so that's why we had it here. For the open circuit, on the other hand, the reflection phase is 0, and that's why S11 is on the right-hand side of the Smith chart. And that is part F of the coax design. So again, out of curiosity, let's look at the field. So again, you would still expect a standing wave because of the reflection, but of course it would be 180 degree apart. So we can animate that, and you will be able to still see the standing wave. Again, there is a null here. In the short circuit, it was 180-degree apart. It was around here, and that's the field inside. And of course, if you make this line longer, you'll be able to see more maxima and minima. Right now, it's a fairly short line. And in terms of the lab report, it doesn't matter what the length of the line that you choose is, but you have to be careful not to make it way too long, so that we don't want you to run a simulation for 3 hours. So make sure it's a reasonable length, but whatever length you choose is okay, as long as you show the results that I asked for. Okay, so we'll go ahead and save the project, make sure everything is good. All right, so the first part of the lab is now done, so we'll move on to the microstrip line. So we'll go to the lab manual. So I'm asking you to design a microstrip line from 1 to 4 on Rogers RO3006 substrate with a thickness of 25 mil. And the first question is, what is the dielectric constant and loss tangent of RO3006? So you can either use Google to find it, or you can actually find it on HFSS, because HFSS has a library of many substrates. And then now, after knowing the dielectric constant, you can calculate the width of the microstrip line needed to achieve a characteristic impedance of 50 ohms. And for that, you can use online calculators like that one. So we'll go on HFSS, find out what the dielectric constant is of RO3006, and then we'll come back to the calculator. Okay, so we can add another design, and we'll call that microstrip. Call it microstrip line. All right, so the microstrip line, we've designed it in the first lab, so this should be straightforward to all of you guys. So we can first add the substrate. And so far we don't know what the line dimensions are, but we can add the substrate, figure out what the dielectric constant is, and then go and calculate the width of the line that we need. So substrate. So for the material, you can go on here and search for Rogers, and you can see 3006 starts to appear. So that's the substrate. The relative permittivity is 3.15, so make a note of that, because we're going to need that to calculate the width of the line. So epsilon r is 6.15. And the loss tangent you can also see under the properties here, so it's 0.0025. Perfect, so select the material. In terms of the dimensions, so the substrate width and length I also did not specify. So again, I'm leaving this up to you guys. Choose a reasonable size that is not too large that the simulation would take a long time, but also large enough so that the fringing fields on the line can be captured. And whatever width or length you choose, you may have to change it later on when you add the coax cable, but that's okay. If you define everything in terms of variables, it's very simple to change after that. All right, so substrate width over 2, 0, and 0. And so I can choose a substrate width to be, let's say, 2 centimeters. So X size will be substrate width, Y size substrate length, and let's say we'll make the length a little bit longer, maybe 4 centimeters. And then the height of the substrate is a defined value, and it's 25 mil. It's 25 mil, not millimeter. And if you type mil here, HFSS would recognize that. All right, so if I press here on the solution space, Control D, you'll be able to see the substrate. And the next step is to design the line, but for that we need the width of the line. So we can go here, click on this calculator. So the dielectric constant of Rogers 3006 is 6.15. the height is 25 mil, so 25 mil. The frequency does not affect the width of the line. The frequency doesn't affect the width calculation because the characteristic impedance does not depend on the frequency. But what the frequency affects in this calculator is the actual length, which is based on the electrical length. So it doesn't matter what the frequency you chooses, you can just use 2. And for the characteristic impedance, we want 50. And electrical length, again, we're not interested in the length of the line, so you can just leave it as any value. And you can synthesize. So here it tells you the width of the line needed to achieve 50 ohms, and the length, again, is not important. It doesn't affect the characteristic impedance. All right, so the length of the line is 0.935, so make a note of that. So line width is 0.935 millimeters. All right, so now we can go back to HFSS and add the line. So we can give that different color so it shows up on top. We will call that the microstrip line. The line dimensions, we wanted to start on the same Y dimension as the substrate, and for X it will be the microstrip width over 2, 0 and 0. No, the Z dimension is the height of the substrate because we want it to be on top of the substrate. The microstrip line width, we just calculated, is 0.935 millimeters. Perfect. X size is the microstrip width. Y size is the length of the substrate. So, and that's perfect. All right. So in case you missed it, the substrate dimensions are here, the microstrip line dimensions are here, and the variables are over here. Perfect. All right, so the next step is to give this line the correct boundary. So in our case, that would be copper. So if you right click, assign boundary, finite conductivity, use material, and we can select copper. And we can give that a name, call it microstrip line. Perfect. All right, so the next step is to add a radiation box because as you guys remember from the first lab, the top part of the line must be exposed in order to correctly operate as a transmission line, and that's what we're going to add next. All right, so radiation box is next, so we can go ahead and add a box. So it can be a vacuum box or an air box. I'm going to leave it as vacuum because it's pretty much the same as air. So that would be, we call that air box. And the dimensions will be the same as the substrate in the XY plane. And then the height would be a little bit higher than the substrate. So 0 and 0. X will be substrate width. Y will be substrate length. And then the Z size, we can create a variable called air H. And again, if you guys remember, this would be, it just has to be high enough above the line. So we can choose something and see if it looks high enough. So if we say, say 4 centimeters, say 4 centimeters. All right, it looks a bit too big. So we can go back and change that to maybe 2. Okay, 2 looks looks big enough, and I'm gonna go and make this more transparent so we can actually see inside. Alright, so now we have the radiation box around. And the next step is to define the radiation boundary around the box, as we've done before. So we want the top side and the top face and the other four faces as radiation boundaries. The bottom, we will define that as copper. So actually, let's first define the bottom as copper. In the previous lab, if you guys remember, we left that end undefined, which means that it was a PEC. PEC and copper, pretty much the same, but I'm gonna go ahead and define this bottom face as copper, so that'll be the ground. Finite conductivity, copper, and we can call that ground so that we know. And so if you go under here, you'll be able to see that ground is the bottom, it's copper, the line is here, and it's also copper. So now we have to define the radiation boundary everywhere else. So this face, this face, this face, and then rotate, and then this face, and then finally this face here. So press F. If you right click, assign boundary and radiation. That's perfect. So every face except the bottom is a radiation boundary. And now the next step is to create the wave ports. So if you guys remember from last time, the wave port is going to go on the microstrip line and has to be big enough in terms of width and height to cover the line. And in the previous lab, I told you that a rule of thumb is that the width and the height have to be 6 times the width of the line and 6 times the height of the substrate. So let's go ahead and do that. So we want to create a sheet. And we'll create that in the XZ plane. So here's the sheet. That one will be wave port 1. And so the position in X, Y, and Z. So here we want to go wave port width over 2, 0, and 0. And we want the width of the wave port to be 6 times the width of the microstrip line. And then the X size will be the width of the port, Z size will be wave port height, and that would be 6 times the height of the substrate. So that's what it looks like. I'm just going to change this to X, Y. And then we can simply copy and paste that here and just move the second one to the other end of the substrate, so substrate L. And that's it. We can then assign those as wave ports, because now they're just it's just sheets. So you can right click on that, assign excitation, wave port, and then that one, assign excitation, wave port. And if you go here, you can see the wave port excitations. All right, the next step is to add the solution frequency. So again, here we're interested in frequencies between 1 and 4. So we can set the solution frequency to 4. We'll set the maximum number of passes to 15 and maximum delta S to 0.01. The minimum number of passes we'll set it to 6, and minimum converge passes to 3. And for the frequency sweep, again, we're interested in frequencies between 1 and 4, and an interpolating sweep is good for that because we don't need the field data. So 1 to 4, and we can leave that as 401. Okay, so I think we have everything we need. So if you go under simulation validate, everything is in the green. Then you can go ahead and analyze all. And just like before, you can look at the solution data conversions as it goes. So here it hasn't run anything yet, so there's no number of passes or elements or solved elements, but you'll see this come as it goes. And you can see here this is already taking slightly longer than the coax cable to converge. We're at 8 passes and still hasn't converged, but it's getting close. You can also look at the plot. You can see that the maximum delta S, which is our convergence criteria, is getting there. So it already passed once. Already finished the 3 target consecutive passes and the simulation is done. All right, so from the lab manual, the first question is to plot the characteristic impedance from 1 to 4. So again, here we want to confirm that the port impedance is actually 50 ohms, which in this case it would take on the impedance of the line. So if the line is 50 ohms, the port impedance would also be 50 ohms. So right click on results, rectangular plot, port Z0, and we want to plot the real and imaginary. And there you go. So it's very close to 50 ohms for the real part, imaginary part is 0. You can also add a marker here if you want to see what the actual number is. So it's 50.3, it's very close to 50 ohms. So that's the first question. The second question is to plot the characteristic impedance. No, we've already done that. Plot S11 and S21 from 1 to 4. So again, go here, S11 and S21 from 1 to 4, because it's the only sweep we have defined. And you can see here the transmission is high, reflection is low. So that's good. The next question is to terminate the microstrip line with a short or a perfect E boundary, and then plot S11 on the Smith chart. So the same thing as before for the coax cable, we're doing for the microstrip line. So again, you can do it on this design, but I prefer to create another design when things change. So you can copy and paste that in the project, and that would be microstrip line short. And the only difference between the other design and this one is we will replace this sheet here, which was a wave port, with a PEC. So I will delete the wave port, but deleting the wave port shouldn't delete the sheet. So the sheet should still be there. See if we yeah. So we deleted the wave port, but the sheet would now be unassigned. So that would be our short, and we can assign that boundary as a PEC. So now we have a PEC. So in this case, we have same thing as before: the ground, the line, and then now we have the PEC here to create this short circuit for the microstrip line, and we have the radiation boundary, of course, and we have this wave port. So we're actually interested in S11 at the short circuit. So again, we have to de-embed the wave port to the short circuit side. So if you right click, or you can just double click post processing, we want to de-embed that to the other end of the substrate, so it will just be substrate L. And that's the beauty of using variables. You don't have to remember numbers, you can simply use the variables when needed. And you can see here that now all the results from the wave port will be de-embedded to this side of the substrate. Okay, so now we can go ahead and run that. conversions as it goes. You can see it went to 15 passes, but it only converged twice. So our target was 3, but it only converged twice. So depending on the design you're running, you may want to go back and run this again for a few more passes to make sure it converges. But since this is a fairly simple design, and you can see that the magnitude of the delta S is going down, I'm not going to run it again. But if you wish, you can go back and increase the number of passes. So you can go back in the setup here and increase the maximum number of passes so that you can make sure it converges. But in my opinion, two convergences after each other is enough. Okay, so let's check the results. So do you expect the port Z not to change? Well, it shouldn't change because the characteristic impedance of the line is not affected by what termination is at the end, so it stays the same. The reflection, would it change? You can see here that it does change. The reflection is very high, as expected, of course, from a short circuit. Now let's plot the results on the Smith chart and see and confirm the location of S11. So as expected, S11 is at this side of the Smith chart, so it's not exactly a short circuit. What you would expect from a short circuit would be a dot like we saw in the coax cable, but it's very close to a short circuit. So this error could be either from the numerical simulation, maybe this is poor convergence, but it also could just be a property of the microstrip line. But as you can see, it's very close to a short circuit. And that's part E. So now let's do the same thing, but instead of a short, we will have an open. So we're going to copy that. And call that open. And now instead of the short circuit at the end, which was a PEC, we're going to delete that. So we're going to delete this, and we're going to assign this sheet, which was a short, we're going to assign it as a PMC. So we'll give it a name open, and then instead of a PEC, we're going to assign it as a perfect H. So that will make this side open. Okay, so let's run that. So going back to the result of the short circuit on the Smith chart, an exercise that you guys can do to make this get closer to a dot or closer to the 0 ohms here, you can try making the wave port here, or not the wave port, sorry, the termination, you can make it slightly smaller so it actually resembles a short circuit, and see if that improves the results. And we'll look at the results of the open and see if we observe a similar behavior. So let's check the conversions. It seems like it's well, it's only converged once. So in this case, if it only converged once, I'm not really sure if it did converge. So I'm going to actually run the simulation again just to make sure. So I'm going to delete the results, clean up solutions, and I'm going to increase the number of passes to 20 passes. And then I'm going to run this again, just to make sure it converged. And that is something that you decide as you work on designs. Different designs will need different number of passes to converge, and that's something you always need to be aware of, that you may have to run the simulation again to get the correct convergence that you need. And let's look at the solution data. Okay, so we're at the 16th path. Okay, and see right there, it had not actually fully converged. So it's a good thing that we rerun the simulation. So it has gone back up here. Okay, it's coming back down. Still hasn't fully converged. So it's got 2 more passes. And we'll see if it converges on those. Alright, so it has still not fully converged even after 20 passes. So if you see something like that, you have to think about what in your design is causing this problem. So we ran this type of simulation. This is the 3rd time so far. The first 2 times the convergence was okay, and now there's a convergence issue. So you immediately think about the definition of this side here, because that's the only thing that changed. So what we can do now is we can look at the results, see if they make sense, and if they don't make sense, then we can go and see if we can change this side to make it work. All right, so since it finished, let's look at the Smith chart. So of course, you would expect from the Smith chart that the S11 will be on the right. So let's see where it is. So it is fairly close to what you would expect, but it's not exactly there, and you know that the convergence is still not that great. So what you can do now is you can say, okay, I'm going to go here and see if I can change this to closely resemble what I'm looking for. So right now, it's a fairly large open or a PMC. So what you can do is you can try to make it slightly smaller and see if that helps. So what we can do here is we can define a new variable and call it PMC width, and we can say that's the same width as the line. And here we'll call that PMC width, and the height we'll call it PMC h, say that's the same height as the substrate. All right, so right now we've changed this open so that it's like right at the edge. So it's just touching the line and the bottom of the substrate. All right, so let's run that again and see if it improves convergence and if it improves the location of S11 on the Smith chart. So let's go ahead and run that. So just by looking at it, it seems like it's going to converge faster, maybe? Nope, it's coming back up. So that seems to still have trouble conversion. But again, we'll look at the results, see if they make sense, and see if we can do something about it. It does seem like there is a downward trend in the conversions. So we'll check the results, and maybe instead of 20 passes, we can give 30 passes to converge. Okay. So let's wait for the frequency sweep to run, and then we'll look at the Smith chart. Okay, so that is not what we expect. So right away you know that something went wrong, because we expect it to be on this side of the Smith chart. So that means the previous case where it was bigger was probably the better case. So we're going to go back and change that to the previous size. And we're going to run that again and give it more time to converge. So we'll or more passes to converge. So we'll give that 25 passes. All right, third time's the charm. So it finished 20, so it has 5 more passes. Okay, so it seems like it has converged three times in a row, and when it does that, it stops. And you guys will notice that as the number of passes gets larger, the simulation will slow down further, and that's because the software is now solving for a much larger number of elements. Okay, so we'll close that, and let's take a look at the results. So again, also the longer the simulation time that it gets to get to conversions, the longer the frequency solution is going to take, because now it's solving for a larger number of elements. Okay, so it does seem like it's not exactly getting to where we expected, but it's fairly close to an open on the Smith chart. So that's acceptable, and we can consider this as a numerical error in the simulation. Okay, so once you have that done, so this is what I'm asking about in part F and the microstrip line design. And once you have that, you can save your designs, and that would be the end of this demo. The next two designs that you have to work on are Coax-Fed microstrip lines for edge mount and vertical through-hole mount, and that will be your part of the lab. I will be available during the lab time as usual for the 3 hours on CULearn, and I really encourage you guys to attend that if you have any questions, because I will be available for the entire time. And these designs are fairly straightforward, but it can take you some time to think about how to implement them. And finally, once you've done that, I have the report guidelines here in the lab manual as well. So please make sure that you read them very carefully before the report, and make sure that you follow the guidelines. And over here I have included everything that I'm looking for in the report for all 4 designs in this lab. All right, and that's the end of the demo, and I will again be available during the lab time if you have any questions. All right. Bye-bye.